Welcome to our first tutorial video for Computer Science 330/Physics 306. So here we have a file named converter.py, and we're going to use this list of functions to solve homework problems in our first homework set. So this is not a class, but it's just a list of functions, so you see all the defined statements, and then in another file we import converter and then just call converter.the function. What does the first function do? Converts decimal to binary. It assumes x is an integer. We start with a list in line 2 result. And so while x is not equal to 0, we append the result of x modulo 2 in line 4. Now x modulo 2, for example, if x was 5, 5 modulo 2 would be 1 because 5 divided by 2 is 2 remainder 1. So the modulo operator just produces the extra or the remainder after a successive number of divisions. And so the other portion of the division problem would be given by line 5 double slash. So x double slash 2 means, let's say x is 5. 5 divided by 2 would be 2. And then the remainder would be given by the modulo operator. So that would be 2 remainder 1. Sometimes this is called floor division or integer division. So 5 divided by 2 in real life is 2.5, but we round down to 2. So you can think of it as a rounding or just integer division. So the algorithm replaces x with x divided by 2 and then saving the remainders. That's the algorithm is lines 3 through 5. But then we have to realize that that means our binary number will come out backwards, because if you divide by 2, then that means that the first digit you find is the ones place and the second division gives the twos place, etc. So reversing the string gives the correct result. So we call result.reverse and then return the list of integers, either they're zeros or ones. In binary to decimal conversion, we expand the weights and the digits of the binary bit string. So we start with line 10, which is just saving the result to be 0, and we're going to add to that total. String number in line 11 uses list comprehension, so we're going to build a list of the digits in the binary bit string. We're assuming here that x is just like as if someone types 1001 into the keyboard, so that's going to be interpreted as a string. But just in case we call the string function on x, so in case the system thought you meant 1011 for 1011, we'll think of that as a string, and then for d in the string version of x, we're going to cast d, the digit, as an integer, and then the brackets build that list into the variable string number in line 11. So list comprehension, a very Pythonic way to solve problems. We have to reverse the list, though, for a different reason. Any loop will start from element 0, but the element 0 in this case would be the most significant bit. And so since we're going to loop over bits, we're going to have to start from the least significant bit in lines 14 through 15, where we're adding to the total 2 to the power of I for I in the range 0 to n. That's technically 0 to n minus 1. So that's given the number of bits, in line 13, where we obtain the length of the string version of the number. That's 2 to the correct power, so 2 to the I, and then times the integer version of the ith element of string number. So that int integer call function call in line 15, where it says int string number I, is you could think of that as redundant, but that's just a safety measure in case there's some weird thing that happens. String number should be comprised of integers. But just in case, we want to make sure that result has the right data type. And so it'll be, the result will be a sum of 2 to the power of 0, 2 to the power of 1, 2 to the power of 2 for the correct number of bits, but then weighted by the zeros and ones. And so that will produce the correct result for the binary to decimal conversion. In line 18, the function max decimal just produces the maximum decimal number that can be represented with a bit string of n bits, and that's just implementation of a formula from the text. Counter is a function that implements decimal to binary conversion, but it actually will count in binary from between the specified range, n and m. So for I in range, this is line 22, I in range n to m plus 1, so that means n to m inclusive. I will iterate between n and m. If I is 0, we're going to want to print just a list of 0, but then once we have, and that's a quirk of Python, because if you pass the number 0 to the function convert decimal to binary, it won't return anything because the while loop will never be entered. So if the while loop is going to run in convert decimal to binary, then we're going to loop over I in the correct range, and then it will spit out the correct bit strings. And so there's a particular problem where we're converting binary numbers between a given range, and it's really binary counting, but this function will do that for you via the for loop. So in line 28, add binary. Here I cheekily punt to decimal addition, so I could first convert the binary numbers to decimal form and then add them and return the result. But you could easily imagine taking that result and using a different function to convert that back to binary. So I sort of drive around the problem of how do you, uh, on a bitwise basis, use convert or add to binary numbers in Python. But that is something you can use bitwise XOR operators to do, as you've seen in the digital labs that we complete. So, uh, so you could implement a different, they could implement this function differently, but for now, this is the way we're doing it, and it works to solve the problems. So, lastly, we need the function one's complement and two's complement. These use list comprehension in line 32, for example, to convert that input x into a string, and then for each element in the string, get the integer digit to build that list, determine the number of bits, and then for each element in the list, 0 to n, we're going to just flip the bit. So if it's equal to 1, for example, in line 35, all the while ensuring that we're dealing with the correct data type, so integer string number I, if that happens to be 1, we need to make it 0 and then continue to the next bit in the bit string. So not just evaluating uh, the string. If you don't have that continue statement there, you get a bug which basically shows you that bits are flipped twice. So you need to make sure that each bit is only flipped once. So the continue statement tells you to do nothing more, and then on the next iteration, think about the next flip. Once all the flips are complete, that's it. The one's complement is just the reversing all the bits, and so you return that string. Two's complement is equal to the one's complement plus 1. So in line 44, we have string number is produced from the one's complement of x, but then um, we form a string and then called string pass, so it's something we're going to pass to a different function. And then for I in string number, which is a list of integers, we're going to add to string pass the ith uh, um, digit, but then we're going to convert from decimal to binary when we're adding two binary numbers, string pass plus 1. So what that does is it pulls off the addition of 1 to the number which has been taken which has had its ones complement computed. So once again, we take string number. String number is the output of one's complement. What's the data type of that? That's going to be a list of integers. So the problem is that the add binary function, which is crucial to computing the two's complement, we need that to be a string. So we're going to form a string for I in string number, string pass plus assign the string version of the digit. We form that string and then add that to 1 with the function add binary, and then we run the convert decimal binary function on that to return the actual binary bit string of the two's complement. So stay tuned for a demo for how this list of functions is used to solve homework problems, and then we'll follow that with a demonstration of wave DROM, which allows you to produce timing diagrams with Python. So we continue with our homework solutions. We're importing converter and also importing SYS, and then implementing the functions in the converter file. And remember, converter file is just a list of functions that does the tasks that we need for this homework set. So we're importing this list of functions, and from that list, converter.convert binary to decimal is called on all of these list elements in this for loop. This is problem 2.2, section 2.2, problem 6. And each subproblem A, B, C, D, E, F, G, H is listed in this list. So we've typed out, the homework exercises we're required to do. And then in this for loop, print converter.convert binary to decimal on the elements of this list. And so to see what that looks like, let's switch over to the terminal. And so we're going to call python3 solutions.py, and then we're going to pipe the output into a program which will allow us to scroll. So you see, we print, the exercise 2.2 number 6, and then problems 1 through A through H are listed here. So the point is, like for example, if you see, okay, the last one is 31, and so that is 32 minus 1, and that's the correct number for having 5 bits. So 2 to the 5th would be 32, so 2 to the 5th minus 1 is 31. So you see that that's being done correctly, and we're just looping our function that does the homework for us over the problems, and that's a perfectly valid way to complete those exercises. To keep things nice and neat, I print, what exercise I'm working with the print function. I call counter, so this one is particularly helpful because you can't. The point of these exercises is to generate the timing diagrams or the lists of bit strings for the binary counting. And in fact, we're going to have a whole a chapter on binary counters at some point. It'll be useful to be able to generate this and perhaps even generate timing diagrams in Python code. So that brings me to my next example, which involves wave DROM. So this is a Python file. First, let me move to the directory where it's located. So I have a number of examples here. I've just listed the gate examples and timing examples. I have lots of little Python scripts. Some of them do timing diagrams. Some of them make gates, logic gates, and complex logic functions. So wave DROM is a way to represent timing diagrams for starters in using Python. So on line 2, we start a long comment or text, which is multi-line, so it uses the triple quotes syntax of Python. And it is a dictionary. So within the dictionary, we have an element named signal, colon, and then there's a list, uh, which is brackets, and you can see I've kept it aligned here. So the signal contains several dictionaries, per line. So it's a list of sub-dictionaries, right? And they have a title, and then so a name, and then it's given, this one is called clock, CLK, and then the wave information is P, and then that repeats. So P, as you'll see, stands for clock pulse. But if you say dot dot dot, it'll repeat whatever you've got there every period. But then there's other waves like data 0, data 1, 2, 3, and you can say low or high, high or low, and have it repeat. Um, then you can give the diagram a header and a footer, for example, and there's things like tick and talk and other symbols that you can put along the header and footer of the image. Once you have that, this is essentially a JSON structure, but it's built into a Python string or paragraph, if you will, because we're using the triple quotes syntax. Then that object is then the argument to a function called render, which will produce an object, SVG, which can be saved as an actual figure. So SVG represents the vector graphic format that can then be saved to disk. So if we run this example, this is timing example 1.py. So we run that. Now there's going to be a file recently created. So I'll just list when it was created. And you can tell that's created September 3rd at 10:14. That's the time you see down here. So this is a new file. And then it's an SVG file. But what we really want is a PDF. SVG can be sometimes hard to view depending on your viewer. So it might be different for different people. Whereas I know PDF will be the same for everyone. So I'm going to use a program that I have for converting an SVG to PDF. You can see the command there. It's a program called Inkscape, but you can also go online and find image converters that will do the job for you as well. So I'm going to run that, and then there's a file, timing example 1.pdf, and that's created just now, right? And let's take a look using this PDF viewer. And so this is what the code produces. So notice that there is the signal clock, as well as the data bits, these 4 serial lines. So the data is 4 bits of data. It's being transferred serially. And then there's enable and not enable being shown down here. So this is what the code produced. It produces a figure that matches exactly the system that you're trying to model, and the talk header and footer just displays 0, 1, 2, so it labels the periods of the clock. So what happens is in this, on the 4th period, so 0, 1, 2, 3, 4th period, suddenly we get data. And then this enable period is high for 3 clock cycles, so this data will be transmitted. And then maybe there's data here, but without the enable, perhaps that data is not transmitted. So, so you can see how this timing diagram would represent a digital circuit that's transmitting 4 serial bits, but only when the enable feature is activated. But that's just, that's one example. There are many examples. Let me show you one example of gates. So let's say just gate example, how about 1 PDF. This is an older figure, but you can see you can actually write code to generate. So let's say you have inputs A and B, and you wanted to take and then not, so that's not and. The symbol you're looking at is an AND gate, but then it's the opposite, is that represents that little circle. And so those outputs are then being fed into this third AND gate with a final inverter, and that's the output. So you could generate both the timing diagram and the actual digital circuit that generates that timing diagram with wave DROM. Last thing I'll say is that there is a nice website for wave DROM, and you can actually run an editor. Without the render function, I mean, it's automatically doing the render function for you, and you're just specifying the structure here. And then that render function is being called on the structure, so you can actually see what happens. Um, so if I can just change something CLK, and so you see it changed the clock, or I can just write, for example, clock, and it'll in real time give you a sense of what your code should do, and that's very useful before entering it into your own code to solve your own homework problems. There's also a tutorial, and it says Hitchhiker's Guide to the Wave DROM. So this page is very thorough, and it talks about making signal groups, header, footer, talking about adding labels for pieces of data that are being sent, um, and then some more fine nitty-gritty details down near the bottom. So the point is, you should learn how to use this software. It's a useful skill for creating digital designs, for communicating what kind of design you're trying to say, you're trying to build to the other person. Without a diagram, a precise diagram, sometimes it's difficult to draw or communicate to the other person what you want them to imagine. So having a system that does this, of course, is very handy. The other thing is that, let's say I copy my uh, timing example like this, right? And now I open, and I'll have to find timing example one dot copy. What if, for example, I change, I have my signal group here, data D0 through D1 through D3. What if I change it to 4, 5, 6, 7, and I could go through the routine to generate that, picture, and all you would see was just the data's labels are being changed. But now if you have an actual file that's responsible for um, generating uh, the design, then you can use the diff command in Linux. And what this will do is it'll show you exactly what's different about the files. So the left-hand file contains, uh, data 0, 1, 2, 3, but the right-hand file has different labels. So this can be used for debugging. So imagine you're designing some large digital function that computes a variety of things or does a variety of tasks. And if you make a change, then of course you're going to want to know what the effect of that change was, or if someone else makes a change, you're going to want to know where the change is, and comparing old and new files is a very efficient way of observing how a particular change causes an effect. So, so that is my example for Wave DROM and the converter list of functions and homework solutions code. For any questions, don't hesitate to email me at jhansen2@whittier.edu. Thanks for your attention.